Hey everyone, and welcome to this in-depth analysis. Today we're diving into a really critical technical breakdown of fiberglass reinforced plastic, or FRP, cable tray systems. Look, if you're an engineer, a specifier, or a project manager dealing with any kind of electrical infrastructure, mastering FRP systems is absolutely no longer optional. It's basically a mandatory requirement for building modern, resilient infrastructure. The margin for error out there is shrinking fast, and relying on old habits, well, that's just going to compromise your structural integrity and completely blow up your project budget. So, let's get right into the data.
FRP cable tray isn't corrosion-proof steel. Now, I know that sounds incredibly basic, right? But honestly, treating fiberglass reinforced plastic exactly like it's just some metal alternative is the single most dangerous baseline assumption you can make as an engineer. When you assume FRP is just this lightweight, rust-proof version of steel, you are literally paving the way for catastrophic, incredibly costly project failures. You see, it fundamentally behaves differently under physical load, under intense heat, and especially under electrical fault conditions.
So here is our roadmap for today's explainer. 1. FRP is not steel. 2. Analyzing specific use cases. 3. Matching geometry to routes. 4. Analyzing common field mistakes. And 5. Actionable steps for execution.
All right, kicking things off with Section 1. FRP is not steel. We need a fundamental mindset shift here.
You absolutely cannot just copy-paste your old aluminum or steel specs and call it a day. First off, let's talk about stiffness. FRP handles physical loads in a completely different way. It flexes entirely differently than steel, which means your support spans, they have to be calculated using a totally different modulus of elasticity. Next up is thermal expansion. FRP expands and contracts at significantly different rates than metallic systems when it's exposed to those extreme temperature swings. If you don't do the math for this, your trays are literally going to buckle or pull apart at the splices. And finally, bonding. Remember, you're dealing with a non-metallic, non-conductive system here. The entire way you approach electrical grounding has to be re-engineered from scratch, because the tray itself is not your equipment grounding conductor anymore.
And because FRP relies on resins, its fire behavior requires a completely different engineering approach too. You simply can't model an FRP system's reaction to fire using your standard metallic system baselines. The smoke generation, the way the flame spreads, and the structural degradation that happens under intense heat, all of this means your fire mitigation strategies have to be custom-tailored to the very specific resin compound you end up selecting.
Moving on to Section 2. Analyzing specific use cases. This is where non-metallic really shines.
Knowing exactly when and where to deploy this material is a real game changer. Let's really analyze some specific real-world environments where FRP drastically lowers lifecycle costs. Take industrial plants, for example, places like chemical processing or wastewater treatment facilities. Metallic systems just degrade so rapidly there. In these environments, FRP wins outright because of its total resistance to harsh chemical exposures, which massively lowers your lifecycle replacement costs. Then you have rail transit. Constant vibration and stray electrical currents are just massive financial drains, but FRP's non-conductive nature entirely eliminates stray current corrosion. What about data centers? Well, there you need high-capacity routing without any magnetic interference. FRP gives you a lightweight, non-magnetic pathway that protects those highly sensitive data lines, all while lowering the structural dead load on the building itself. And finally, in commercial buildings, FRP's extremely lightweight profile drastically speeds up the actual installation process, driving down those historically high initial labor costs. In every single one of these demanding sectors, specifying FRP properly lowers the overall lifecycle cost quite dramatically.
All right, Section 3, matching geometry to routes. Are we going ladder, perforated, or solid?
Let's break down how we actually map geometry to specific route conditions, because you generally have three main options: ladder, perforated, or solid bottom. So, which one fits your specific route? Well, if your route condition demands maximum ventilation, you're running heavy power cables, and you've got long support spans, an open ladder design is exactly what you need. It allows all that heat to dissipate rapidly. But what if you're routing smaller, really sensitive control cables? Cables that need physical support along their entire length, but still need a bit of airflow? That is when a perforated geometry becomes structurally required. And finally, if your route happens to pass through an environment where those cables have to be protected from dripping liquids, falling debris, or specific environmental contaminants, a completely solid bottom geometry is pretty much mandatory. You always have to match the physical shape to the physical threat.
Okay, Section 4, analyzing common field mistakes. Basically, the 6 pathways to failure.
When the fundamental properties of FRP get ignored out in the field, you generally run into 6 main pathways to failure. But 3 of them, they stand out as absolute project killers. Number 1, overextended spans. Because engineers sometimes just assume it has the stiffness of steel, they place their supports way too far apart. This leads directly to severe tray sagging and eventually cable damage. Number 2, specifying the wrong resin for the exposure zone. If you put a standard resin into a highly corrosive chemical zone, it is going to fail, no question. You absolutely must match the resin chemistry to the exact environmental threat. And number 3, grounding problems showing up late in the project. Because the tray isn't conductive, grounding has to be planned independently. When installers wait until the very end to figure out their bonding, you get massive delays and huge safety hazards. And again, notice how all of these stem from that one core sin we talked about, treating the FRP material like it's just steel.
This brings us to Section 5, actionable steps for execution. Let's get into the flawless field procedure.
Think of this as your ultimate engineer's checklist for a truly flawless FRP installation. We want to summarize these actionable steps clearly. Step 1. Adjust your span calculations right now. Throw out the steel charts entirely and calculate based strictly on the FRP manufacturer's specific load data. Step 2. Select zone-appropriate resin. You need to audit your chemical, UV, and fire risks, and then match the precise resin compound directly to that zone. Step 3. Implement early grounding. Design your separate grounding conductor pathways during the initial schematic phase. Please do not treat bonding as an afterthought. And Step 4. Account for thermal expansion. You have to mandate expansion splice plates at mathematically calculated intervals to absorb the natural shifting of this material. Seriously, execute these 4 specific steps and you'll eliminate the vast majority of field failures.
And of course, proper execution also extends to your procurement phase. You absolutely must specify systems that strictly adhere to global safety and manufacturing standards. Specifically, we're talking about IEC 61537, NEMA VE1, BSEN 500085, and GB 31251. Now, manufacturers like Xinma, who produce these comprehensive cable management solutions for everything from data centers to industrial plants, they actually engineer their products to meet these exact rigorous standards. If the product you specify doesn't carry these compliance certifications, your entire execution plan is fundamentally compromised right from day one.
So that brings us to the final, really critical question you have to ask yourself and your team today. Are you treating your next FRP installation like steel? If your answer is yes, or honestly, even if it's maybe, it is absolutely time to halt the process and apply the actionable framework we just covered. Stop assuming, start calculating for the material's actual properties, and build infrastructure that is truly meant to last. Thank you so much for joining me for this breakdown. Take this checklist, apply it to your current specifications, and I'll see you in the next analysis.